Before we do some examples on friction force, I want to talk about a particle moving on a curve versus a particle moving on a surface. So let me consider a particle on curve and then particle on surface. So a particle on a curve looks like this. We have some random curve and we have a particle moving on it. Whereas a particle on a surface is that we have some random surface and then we have a particle moving on it. So a curve has one tangent direction. You can call it ET, and then two normal directions, EN and EB. So one tangent, two normals. So always the particle is free to move in the tangent directions and cannot move in the normal directions. Okay, so in the plane we have one normal direction that the particle cannot go into, and that's perpendicular to the plane, but the particle can move in the plane. That's right, the two tangent vectors in the plane is T1 and T2. So depending on your basis, they can be E1, EX and EY, E1 and E theta. So we have two tangents in the plane and one normal. Now, if I want to draw the free body diagram of the particles in each case, in the first case, the particle moving on a curve, if I have the normal force, it's gonna have two components along the two normals, NN, EN, plus NB, EB. Why? Because the particle is constrained from moving in both of these directions. So there should be forces in these directions forcing the particles to remain on the curve. Along ET, there is no normal force, but if there is friction, the friction force is gonna be along ET. Okay, if the friction is kinetic, then the relative velocity is gonna be along the curve, along ET. Now, in the case of a particle moving on a surface, then the normal force is just gonna be along N. And the friction force can have two components in the plane. Component along E1, EX, T1, and the component along T2. So basically in the plane. And to keep the color coordination going, we'll color this in red. Okay, I failed. But so these two components, N and B, for example, here, they're not necessarily equal. And the magnitude of the normal force is the square root of NN squared plus NB squared, because EN and EB, they're part of an orthonormal basis. So again, the friction force is always tangent to the path. A curve has one tangent, a surface has two tangents, and the normal force is normal to the path. A curve has two normals and the surface has one normal. Let us look at the examples actually. Let me look at examples from here. so I'm failing at downloading this, but let me look for example here. So this is a particle that is on the surface of the table. So it has one normal direction. If I take EZ to be along the axis of rotation, EZ to be along the axis of rotation, it's normal to the plane, and then ER and E theta are both tangent to the plane. So if I want to write a normal force, it's gonna be along EZ, and friction forces, they're gonna be along ER and E theta. So this is a particle moving on a surface. The normal force is along the normal to the surface, EZ, and the friction forces are along the tangents to the surface, ER and E theta. Let us consider another example. For example, here we have a particle that is sticking to the surface, the inner surface of the cylinder. But in general, the particle is free to move inside the surface of the cylinder, on the inside surface of the cylinder. So again, the cylinder is rotating. EZ is going to be along the axis of rotation, and ER is going to point like this. E theta is going to point into the page, so that ER cross E theta is EZ. Because remember that in cylindrical polar coordinates, we draw our position vector from the origin to the particle. EZ is always along the axis of rotation perpendicular to ER and E theta. And then to draw ER, we project R into the horizontal plane, and we draw ER along that. And E theta is such that we complete the triad ER cross E theta is equal to EZ. So in this case, again, it's a particle moving on a surface. Now, what is the normal to the surface? The normal to the surface is ER. And then E theta and EZ, they're both tangents to the surface. So then the normal force, N, is NR-ER. And the friction forces, F theta E theta plus FFD EZ. So I hope these two examples can illuminate what's going on. So particle moving on surface. Okay. Let me see if there are any examples of a particle moving on a curve. This is more like moving, well, let me give an example. So previously in one of the lectures, we talked about a particle in a tube. So we have a particle of mass m in a tube, and the tube is rotating about some axis perpendicular to the page. And so EZ is that axis of rotation. And we have ER and E theta. So the particle can move along ER, but it cannot move along E theta and EZ, because if it's concentrated inside the tube. So the friction force in this case, if it were to be, would be along ER, the direction of motion of the particle. And then the normal force, we did this before, has components both along E theta and EZ. So this is a particle moving on a curve. The particle is just not free to move on any surface. It needs to move on this just path inside the tube while the tube is rotating. So the normal force has two directions, along E theta I think a more intuitive example of a particle moving on a curve is a person on a roller coaster. So just some curve, that is the roller coaster, and this is a person riding the roller coaster. So this person can, inside a wagon, of course. So this person can move along ET. There might be friction in this direction, and they're constrained from moving along EN and EB. So then normal forces are in these directions. So this is ET, and EN and EB are perpendicular. I probably should do EB, EN to make it the right-handed basis. But you get the point. Okay.